Hello students, good afternoon. Last time we were discussing about time shifting. The next property of Fourier transform is duality or symmetric property. If x of t, Fourier transform of x of t is x of f, then shape of signal in time domain and shape of signal in frequency domain can be interchanged. If Fourier transform of x of t is x of f, then this x, this capital X represents the shape of signal in frequency domain, and this small x represents the shape of signal in time domain. So, if Fourier transform of x of t is capital X of f, then this shape of time in time domain is interchanged with shape of signal in frequency domain. Proof x of t is given by integration minus infinity to plus infinity x of f exponential j2 pi ft dt, and this is inverse Fourier transform. So, to prove duality or symmetry property, start with IFT and substitute minus t in place of t. So, x of minus t is equal to minus infinity to plus infinity x of f exponential minus j2 pi ft df. Then interchange t and f to get this expression. T is changed by f, here f is changed by t, f and t is changed, and this f is changed by t. And this is the expression of Fourier transform of capital X of t. Fourier transform of capital X of t. So we can prove that x of t is equal to shape of this signal. Shape of signal is changed with the shape of signal in frequency. Shape of signal in time domain can be interchanged with the shape of signal in frequency domain. Interchanging of variable is possible because Fourier transform is definite integral and variables of integration are demi-variable. Question based on duality property. If Fourier transform of exponential minus t ut is given by 1 by 1 plus 2 j2 pi f, then prove that Fourier transform of 1 by 1 plus j2 pi t is equal to exponential f u of minus f. Here we use duality property. In duality property, first we take inverse Fourier transform, then we replace t by minus t and interchange t by f. So Fourier transform of exponential minus t ut is given by this. So we can write x of t or exponential minus t ut is written as integration minus infinity to plus infinity 1 by 1 plus j 2 pi f multiplied by exponential j2 pi ft df. This is inverse Fourier transform. Then replace this t and this t by minus t. So we get exponential t multiplied by u of minus t is equal to integration minus infinity to plus infinity exponential minus j2 pi ft divided by 1 plus j2 pi f d, and then interchange t by f. Changing t by f, this t is changed into f, this t is changed into f, and f and t is changed here. This f is changed into t and this f is changed into t. So this expression is simply this expression is Fourier transform of 1 by 1 plus j2 by t. Fourier transform of this is equal to exponential f u of minus f. So in proving any improving duality property, we can simply start with inverse Fourier transform or x of t, then replace t by minus t and then interchange t by f, and we get the desired result. Next property is frequency shifting property of Fourier transform. If Fourier transform of x of t is x of f, then if we multiply x of t by exponential j2 by fc t, then the frequency spectrum is shifted by minus fc. Take the Fourier transform of this, and according to the definition of Fourier transform, we get the expression integration minus infinity to plus infinity exponential j2 pi fct x of t exponential minus j2 pi f t dt. And if we simplify this expression, we get this expression, and this is the Fourier transform. In this, Fourier transform is given by x of f minus fc. It means that if we multiply time domain signal by exponential j2 pi fct, then the whole frequency spectrum is shifted right by fc in the frequency domain. Next property, area under x of t. This property states that the area under the curve x of t is equals the value of its Fourier transform at f is equal to 0. If we want to find the area of x of t, then calculate the Fourier transform of x of t and substitute in that Fourier transform f of is equal to 0. Fourier transform of x of t is equal to x of n, and we know that area under x of t function is given by integration minus infinity to plus infinity x of t multiplied by dt. Clear? And this is the area of x of t, and in this expression, if we multiply exponential minus j omega t or minus j 2 pi ft at f is equal to 0. When f is equal to 0, this exponential term is exponential 0, and exponential 0, value of exponential 0 is 1, so we can easily multiply it by this expression, and this is the formula of x of f at f is equal to 0. So to calculate the area of x of t, we can either find out x of t, Fourier transform of x of t, and substitute f is equal to 0. Or you can say that if you calculate the value of f of x of f at f is equal to 0, and that is the area of signal x of t. Similarly, area of x of f. X of f is, this is the Fourier transform of x of t. Then calculate the area of x of f. Area of x of f is given by this expression integration minus infinity to plus infinity x of f df. And if we use IDFT, x of t is given by integration minus infinity plus infinity x of f exponential j2 pi ft df. If in this expression, if t is 0, then this exponential 0, value of exponential 0 is 1, and this is the area of x of f. So we can say that the area of x of f equals to the value of signal x of t at t is equal to 0. Value of signal of x of t at t is equal to 0. Show that total area under the curve of same function is equal to 1. That means integration minus infinity to plus infinity sin of t dt. This is the area of same function, and you have to prove that area of same function is equal to 1. We can multiply this function by exponential minus j 2 pi f t when f is equal to 0, because this term is equal to the 1, and area of same function is given by this, and we know that Fourier transform of same function is rectangular function, and sink of t is equal to rectangle of f, and area of sink function is given by rectangle of f when f is equal to 0. F is equal to 0. When f is equal to 0, value of this rectangular function is 1. So we can say that area of same function is 1. Differentiation in time domain. X of t using IFT. X of t is given by integration minus infinity to plus infinity x of f exponential j 2 pi f ft df, and differentiate this x of t, we get dx of t by dt, and d by dt of this, differentiate this quantity x of f is, and if we differentiate this with respect to time, we get x of f multiplied by j 2 pi f exponential j 2 pi f t df, and here we can say that this term is the Fourier transform of x of dx by dt. This is the inverse Fourier transform. So we can say that Fourier transform of dx by dt is equal to j 2 pi f x of f, and it is written, and we can also say that differentiation will enhance the higher frequency component, because the mode of or magnitude of this is greater than magnitude of x of f. Or we can say that differentiation in time domain when we have dx by dt is equivalent to the multiplication of its Fourier transform by j omega. If we take the Fourier transform of differentiation of a signal, then this Fourier transform of differentiation of a signal is equal to its Fourier transform multiplied by j omega. Frequency differentiation. In frequency differentiation, x of f is given by exponential integration minus infinity to plus infinity x of t exponential minus j 2 pi f t dt. And if we differentiate this with respect to f, we get minus j 2 pi t. We get this expression. So we can say that differentiating in frequency domain, x of t means signal in time domain is multiplied by minus j 2 pi t, or if here in this case d x of f by df is, and in second case d x of omega by d omega. In this case, this time domain signal is multiplied by simply by minus t, minus j t. Integration in time domain. Integration in time domain, x of t is given by differentiation integration of x of lambda by d lambda, taking the Fourier transform of both sides. Fourier transform of x of t is x of f, and Fourier transform of this differentiation is equal to j 2 pi f multiplied by Fourier transform of integration minus infinity to 2 x of lambda d lambda. So we can say that Fourier transform of integration is equal to x of f divided by j omega, or integration suppresses the high frequency component. Differentiation enhances the high frequency component, and integration suppresses the high frequency component. Convolution in time domain. If two time domain signals are convoluted in time domain, then their Fourier transform will be multiplied in frequency domain. x1 t of t convoluted with x2t, and this is given by integration minus infinity to plus infinity x of lambda, x of x1 of lambda, x2 of t minus lambda d lambda, according to the definition of convolution. And if we take the Fourier transform of both sides, then, and if we assume that this is x of t, so integration minus infinity to plus infinity, this is x of t multiplied by exponential minus j 2 pi f t dt. Multiply and divide by exponential minus j 2 pi f lambda, and if we take x1 of lambda outside this integration, we get this expression, and this is, in this expression, t minus lambda is replaced by m, t minus lambda is replaced by m, so we get, this is the Fourier transform of x1 lambda or x1 t. So this expression is written as x1 f, and this expression is also written as x2 f. So if time domain signals are convoluted in time domain, then their frequency domain signals are multiplied in frequency domain. Multiplication in time domain. If two time domain signals are multiplied in time domain, then their Fourier transforms will be convoluted in frequency domain. Taking the Fourier transform of two multiplied signal x1 t multiplied by x2t, if we take the Fourier transform of this according to the Fourier transform definition of Fourier transform, we get this expression. And if by the definition of inverse Fourier transform, x2t is given by integration minus infinity to plus infinity x2 of f1 dash exponential j2 pi f1 dash t df1 dash. Then substituting the value of x2 t in this expression, we get this expression, and joining these two terms, we get this expression, and this f minus f dash, if we replace this f minus f dash by tau and rearrange this equation, we get, if f minus f dash is tau, then this f dash is replaced by f minus tau and exponential minus j 2 pi tau t d tau and dt, and this expression, if we separate this term and this term, we get exponential minus infinity to plus infinity x2 of t minus tau d tau integration minus infinity to plus infinity x1 t exponential minus j 2 pi tau t dt, and this is the Fourier transform of x1 tau, and this is the convolution of x1f convoluted with x2f. So if time domain signals are multiplied in time domain, then their Fourier transform will be convoluted in frequency domain. Determine, there are some questions based on Fourier transform. Determine Fourier transform of ut. Determine Fourier transform of ut. This is given signum t. Signum t, if we add 1 in this signum t, 1 plus minus 1 is 0 and 1 plus 1 is 2. It means that if we add 1 in signum t, we get this signal, and if we divide this by 2, we get unity step. So we can say that x of t is equal to ut is equal to signum t plus 1 divided by 2. We write this ut in terms of signum t. So ut is equal to half plus signum t divided by 2, and if we take Fourier transform of both sides, then we know that Fourier transform of ut is written as x of omega, and this is constant. We know that Fourier transform of 1 is equal to 2 pi del omega. So if for constant value, the Fourier transform of constant value is 2 pi k del omega, and here value of k is half, so we get 2 pi half multiplied by del or delta omega plus Fourier transform of signum t is given by 2 by j omega multiplied by half, and this is the Fourier transform of ut or unit step function. Find the Fourier transform of x of t. X of t is given by this rectangular function. X of t is given by a is magnitude or amplitude of this rectangular function, and r, this t T is duration of rectangular signal, and so this is the duration of rectangular signal. Previously this question is solved, but in this question we solve this question by using the property of Fourier transform. There is constant value in this region. So if we differentiate this region, we get 0. In this region, there is a constant value. If we differentiate this region, we get 0 value. But there is a step from 0 to A. And this is a step of A. And we know that if we differentiate any step function, we get an impulse function. So this impulse function is given. A is the weight of this impulse function, and this impulse function is situated at minus t by 2. So we can write that A delta t plus t by 2. Similarly, in this case, initial value of the function is A, and at this value of 0. So 0 minus A, weight is minus A, and this delta function is situated at t plus 2 t by 2. So we can say that this impulse function is given by minus A del t minus capital T by 2. And this is x of t, dx by dt. So dx by dt is written as A del delta t plus t by 2 minus A delta t minus t by 2. We can write this equation, and taking the Fourier transform on both sides, since this is the differentiation of x of t, x of omega is multiplied by j omega, and in this case A is constant. Delta t, Fourier transform of delta t is 1, and this is shifting. Due to this shifting, this term appears exponential j omega t by 2. Similarly, this minus sign, this is the minus sign for this minus sign, and delta t, Fourier transform of delta t is 1, and this is shifting. For shifting, we get exponential minus j omega t by 2. And if we rearrange this equation, we get final this equation, and it is equal to 2a by omega sine omega t by 2. And if we rearrange this equation, we get at sine omega t by 2 divided by omega t by 2. And we know that sine x by x is equal to sampling function. So we can say that x of omega is equal to at sampling of omega t by 2. So Fourier transform of rectangle t by t is given by at, means this at is multiplied by duration multiplied by sample of omega t by 2. Find the Fourier transform of rectangular pulse shown in this figure. In rectangular pulse, then x of omega is given by integration minus t by 2 to t by 2 rectangle t by t exponential minus j omega t dt, and value of rectangular pulse is 1. So here we get 1, and if we integrate and substitute the limit, we get 2 by omega sine omega t by 2, and rearranging we get t multiplied by sine omega t by 2 divided by omega t by 2, and this is sampling function. So Fourier transform of this function is equal to t sample of omega t by 2. Then find out the Fourier transform of g of t. Fourier transform of g of t is simply for Fourier transform of x of t minus t by 2. This function is shifted, this rectangular function is shifted to the right by t by 2. So this is written as this, and Fourier transform of time domain shifted function is given by exponential minus j omega t by 2 multiplied by x of omega, and x of omega is given by this. Clear? इसमें क्या करना है, तुम्हें फाइंड आउट करना है इसका फोरियर ट्रांसफॉर्म, और इस शिफ्टिंग प्रॉपर्टी को यूज करके इसका फोरियर ट्रांसफॉर्म लिख सकते हैं. Then find out the Fourier transform of signum t is equal to x of t. इसको भी प्रूव किया हुआ है पहले, but in this case we will use the property of Fourier transform. This is a constant. If we differentiate this, we get 0 value. If we differentiate this x of t, we get 0 value. But here, initial value is minus 1, final value is 1. It means that weight of impulse, there is a jump. This is jump. Jump means unit step function, and differentiating unit step function, we get a delta function. And weight of this delta function is 2. So we get x of t, x dx by dt is drawn by this diagram. Dx by dt is given by 2 delta t, and taking Laplace transform on both sides, we get j omega multiplied by x of omega is equal to 2, because Fourier transform of delta function is 1 and x of omega is 2 by j omega. And we know that Fourier transform of signum t is given by 2 by j omega. Last two questions. Find the Fourier transform of x of t is equal to del t plus 2 plus del t plus del t minus 2. And we know the shifting property of impulse function. If any function is multiplied by impulse function, then this impulse function shift the signal at t is equal to 0. So if we take the Fourier transform of both sides in this question, then we get x of omega is equal to integration minus infinity to plus infinity, and this x of t is multiplied by exponential minus j omega t dt. Due to this impulse function del t plus 2, this f of x of t is shifted as t is equal to minus 2. This function is shifted as t is equal to 0, and due to this delta function, this function is shifted at t is equal to 2. So if we substitute the value of t is equal to minus 2, we get this value, and this is simplified form of x of omega. And next is x of t is given by d by dt, and this. We know that if we differentiate unit step function, we get impulse function, and if we differentiate this unit step function, we get an impulse function situated at minus 2 minus t, and magnitude is minus 1. तो हम इसको ड्रॉ करोगे तो ये मैग्नीट्यूड तुम्हारा माइनस 1 आएगा. पहले इसको ड्रॉ करना और देखना, तो ये मैग्नीट्यूड तुम्हारा माइनस 1. Similarly, if you differentiate this unit step function, you get impulse function or del t minus 2. So if we take Fourier transform of both sides, then we get x of omega is equal to this, and due to impulse function, this function is shifted at t is equal to minus 2, and this is shifted at t is equal to 2, and we get this final expression. Last question is, before discussing this question, you know that any periodic function can be written by Fourier series. Any periodic function can be written by Fourier series as x of t is equal to summation n from minus infinity to plus infinity a n exponential minus j plus j n omega t, where omega is given by 2 pi by t, and value of a n is given by this. The question is, find out the Fourier transform of this impulse train. Previously, you have find the Fourier transform of single impulse train or a periodic function, which is a periodic function. In this case, we have to find out the Fourier transform of impulse train, and this is periodic function. This impulse train can be written as x of t is written as delta t plus delta t minus capital T, delta t minus 2t plus delta t plus capital T, similarly plus delta t plus 2t, and so on. So we can write x of t as summation from minus infinity to plus infinity delta t minus n. This x of t is summation of impulse function and its shifted version of impulse function. Since this is periodic function, first we calculate the value of an. An is given by 1 by t, and x of t is simply impulse function, and this impulse function shifted this impulse function shift this function at t is equal to 0. So exponential 0, value of exponential 0 is 1. X of t dt, this is the area of impulse function, and area of impulse function is 1. So value of an, Fourier coefficient, is 1 by t. So x of t is written as, by this formula, x of t is written as summation from minus infinity to plus infinity 1 by t exponential j n omega t, and this 1 by t is constant. We take this 1 by t out of the summation, and taking Fourier transform of this side and this side, we get x of omega 1 by t summation minus infinity to plus infinity and Fourier transform of exponential j n omega naught t is given by 2 pi delta omega minus omega naught. Yeah. And this 2 pi by t is written as omega naught and Fourier transform of periodic impulse train is given by z. And this is drawn in this figure. Impulse function. This impulse function is a periodic function. Impulse function, Fourier transform of this impulse function is simply a DC value and whose magnitude is 1. Clear? And if this aperiodic signal is converted into periodic signal, then their Fourier transform is simply the sampling of or sample of this function. So we can say that if a periodic signal is converted into periodic signal, then sampling of Fourier transform of a periodic signal, we will get the Fourier transform of periodic signal. So इसका क्या मतलब है यहाँ पे, ये अपीरियोडिक सिग्नल है, इसका पीरियोडिक सिग्नल, इसका फूरियर ट्रांसफॉर्म जो है वो डीसी सिग्नल। अगर इस अपीरियोडिक सिग्नल को जो है चेंज कर दिया, पीरियोडिक सिग्नल में कन्वर्ट कर दिया, देन द फूरियर ट्रांसफॉर्म ऑफ दिस पीरियोडिक सिग्नल इज सिंपली द सैंपल ऑफ sampling of Fourier transform of a periodic signal. Clear? Hello. आरू
मैम
क्लियर हुआ? हेलो,
क्या क्लियर?
ये यहाँ पे जो मैं बता रही हूँ तुम्हें क्लियर है? ओके, टाइम इज ओवर, थैंक यू।